Okay, welcome everyone. It's a great pleasure for me to introduce this lecture within our course. This is our week 12, and we have today Professor Peter Diggle with us. You have heard about him already in this course, but now we have the pleasure to have himself delivering our first lecture today. If you go to the website at Lancaster University, you'll find the vast CV of Peter. He is now a distinguished professor at the University of Lancaster, in the Faculty of Health and Medicine, and related to the group CHICAS, where they develop lots of researches within this area. He's also Director of Training of Health Data Research in the UK, and has adjunct positions within other universities like Johns Hopkins, Yale, and Columbia University in the US. Peter was the president of the Royal Statistical Society fairly recently, and he has a wonderful and long track of research records, including several papers and books and prizes he have won throughout his very productive career. He's also related with the main statistical journals within our field. So I'll make this description available to you, but I have my own here. Besides having hundreds of publications on statistical and subjective specific area journals and several books, large number of projects with collaborators and research students, and a must-see talk, which is his presidential address to the Royal Statistical Society, I think the best description I can find of Peter, especially in today's, the current times we live, is the word super spreader. People talk about super spreader a lot during these days, and I'm very comfortable to say that Peter is a super spreader of science and scientific minds. And I say scientific minds because I know from him that he's very proud of having a vast number of students who worked with him throughout his career. So that's my best definition or introduction to Peter, to yourselves. And also, I'd like to point some of his books, and you can see here a collection of them. And there are some nice things about these books and some things which make connections with today's lectures. There is something in common between most of these books, in particular the ones in the bottom and the two ones on top, the ones I'm marking here, which all of them somehow have their main subjects in modeling correlations, being time series in longitudinal data analysis or spatial data analysis. Correlation is a key issue, and he's really a word authority in the field. And besides of that, for this course in particular, we have already mentioned several times this particular book he wrote with Amanda Chatwin, which is an inspiration for our course. And as I mentioned before, we have a lecture based on the book, in a particular chapter of the book. But I can say that I have been inspired a lot by the examples, the way to conduct different subjects that we can see in this book. It's one of my favorite books. I read it again and again, and it's really much connected with our course. And for today's lectures, there is a particular book which is Longitudinal Data Analysis that he co-authored with Patrick Hatgary, Kung Il Yang, and Scott Zeger, which is a really must-read book in the field. It's one of the key references in longitudinal data analysis for many years now, and it's very important. In 2 weeks' time, Peter will be with us again, and at that time, he will talk about things more connected with spatial statistics, which is the main topic behind all of these 5 books I marked here in the bottom. So that's a quick introduction, and before I hand over to Peter, I'd like to share with you, Peter, some of the information the students provided us about today's subject. I placed this first question in a kind of not ideal way, but we can see that something between 10 and 20% of them are comfortable to define what longitudinal data analysis is. And in the second question here, I asked them whether they have came across with longitudinal data analysis in papers or talks within their area. And more or less 27% said yes to that. And I also asked them whether they have already analyzed some data with such kind of structure, either being longitudinal or at least repeated measures. And nearly 10% said that they already did. And finally, I asked them whether they can anticipate if longitudinal data analysis will be used within their research studies during their PG programs. And 5% said yes for sure, 8% are not yet sure, and 15% thinks that they are not using such methods. So with this, Peter, I'd like to say thank you very much for being with us, and the audience is yours. If you can share your screen or stop sharing mine here.
Thank you very much, Paulo. That was far too generous, but it's certainly a real pleasure for me to be here. Well, I really want to thank you all for actually letting me join this course. My connections with Brazil date back 20 years, well, more really. My first visit to Brazil was 20 years ago when I visited Paulo and Silvia Shimakura after several very rewarding years for me, in which I was supervising Paulo in his PhD. And since then, I've developed both personal affection and professional connections with the country. And I'm currently working in the north of Brazil, in Salvador, in Bahia state, looking at some of the public health problems in the favela communities in that city. And I very much hope, as I said to Andre before we started, that I'll be able to visit Brazil again next year in easier times for us all. Paulo has also said so far that everything that I'm talking about is in this book, which was co-authored with 3 American colleagues, based in America, Patrick Hegarty, Kung-Il Yang, and Scott Ziegler from Johns Hopkins University. I'm well aware that the audience comes from a wide range of academic disciplines, and I've tried to pitch the lecture so that there will be something in it for everyone, but I'm certainly not assuming that anybody in the audience is already an expert in longitudinal data analysis. So I want to use this example throughout the lecture to explain what longitudinal data is and to discuss some of the challenges in analyzing longitudinal data efficiently in order to answer substantive research questions. So I believe very strongly that statistics is the servant of science, and that it's not for statisticians to state questions, it's for statisticians to answer other people's questions. So this example has its roots in the pharmaceutical industry in America, in which the company concerned was interested in comparing the effectiveness of their, at the time, novel drug, risperidone, against a then standard drug, haloperidol, and, as is often the case in drug trials, a placebo, which is, if you like, just a sugar pill, to understand how regular administration of any one of these 3 drug treatments over a period of time would improve the symptoms of chronic schizophrenia patients. Schizophrenia, as I'm sure you know, is a serious and debilitating mental illness. And to the best of my knowledge, it is rarely, if ever, cured, but there are ways of alleviating the distressing symptoms that the patient suffers. And so the study was designed as a randomized trial in which volunteers were allocated at random amongst these 3 treatment groups. And the first thing you will notice is the discrepancy between the number on the novel therapy, risperidone, and the numbers on the standard therapy. This was in fact because the novel therapy, because it was novel, was being tested at different dosages. And for the purposes of this lecture, I've simplified the presentation so that we only have 3 treatments pooling all of the different risperidone doses. Because we're dealing with a chronic condition and our goal is to alleviate symptoms, we don't just measure symptoms once, we measure them at baseline, 1 week later, another week later, another 2 weeks later, another 2 weeks later, and finally at 8 weeks since randomization to one of the 3 drug treatments. And what we're measuring here is a standard psychometric instrument. These letters in English stand for positive and negative symptom scale. So this is basically a number that is derived from an extensive interview with each patient in which they are invited to describe their current symptoms, both in terms of symptoms that they feel good about, like being able to cope with the world and feeling happy, and symptoms they feel bad about, like being sad or frightened or debilitated in some other way. What that should, of course, warn you is that this is not a measurement like weighing a person on a scale and concluding that they weigh 83 kilograms. You would have to expect quite a lot of noise in measuring something like this, because I could imagine, and I think you could imagine, that if you took the same patient and asked them to fill in the questionnaire twice or to be interviewed twice, you might well get a different answer. And so you have to expect that these data will be somewhat noisy, and this is why it presents a challenge to the statistician in analyzing them. Another challenge that presents itself to the statistician is that when you measure the same thing on the same person over a period of time, the early measurements are probably going to be somewhat predictive of the later measurements. So that if you notice over the first few measurements that a particular patient is suffering from symptoms more severe than the average of the people in the trial, you might well predict that that would continue, that they are intrinsically a high responder. High is bad here because it's symptoms, right? Also, if you measure the same patient over time, you are not expecting to see the same number for the same reason that if you measure them twice at one time, you'll get different numbers. So there are many different sources of variation in these data that we're going to have to take account of. And the final thing to notice from this table is these numbers are the people who provided data. And at baseline, when the patients were randomized, there were some 518 patients in the trial. And most of those provided a follow-up measurement 1 week later. So we got an initial indication of the variability between patients and within patients between times. But in order to monitor their longitudinal process over a longer period, we encountered a very common feature of longitudinal data, which is the phenomenon usually called dropout. And dropout means that these patients failed to complete the study. Now, there can be many reasons why patients do not complete a study of this kind, but in this case, an obvious one is that the patient may become disenchanted with their experience of the study. So that, for example, and this is a hypothesis that we will see has some validity, if patients perceive that the treatment is not giving them any benefit, they may withdraw their consent to continue in the trial. And this has, as we shall see, a rather fundamental effect on not just how we should analyze these data, but more critically, how we should interpret the results of the analysis. And the reason for that is because the goal of any statistical analysis is to answer somebody else's question. And the question in this case is the drug company's concern to know whether their treatment is more effective in treating chronic schizophrenia patients than the then standard, beg your pardon, this is the novel, than the then standard haloperidol, and the placebo is there to make the trial more robust in the sense that if simply being under therapy has a beneficial effect, then you would expect to see the placebo patients also improving their responses during the course of the trial. So here is my first picture of the data. And the one thing that I think you would all agree with in this picture is that it confirms what I said a couple of minutes ago, that these data are very noisy. So the color coding refers to the 3 treatments. The x-axis is the time since randomization, and the y-axis is the response of this questionnaire instrument. And remember that high values are bad news for the patient. Well, it's tempting to look at those that picture and say, well, there's not a lot of action there. It all looks very noisy. And I wouldn't be too upset if a first-year undergraduate student analyzed these data and concluded they could draw a horizontal line through the whole lot and say it's just a lot of noise and not much is happening. But this is not a very useful way to plot longitudinal data, because it fails to recognize the connectivity in the sense that one of these blue points is associated with a particular blue point here, and another particular blue point there, and another particular blue point there. And so this picture conceals quite a lot of structure, the most basic structure being that longitudinal data include repeated measurements on the same subjects, and they often behave in a statistically different way to measurements taken at different times on different subjects. So we can do something very simple with these data, which is simply average the response under each treatment group at each time. So since we have 1, 2, 3, 4, 5, 6 times, okay, and 1, 2, 3 treatment groups, what you have here is a visualization of 18 different averages. In each case, it's an average within a particular one of the 3 treatments at a particular one of the 6 times. Now, this is a picture that causes the drug company some more pleasure, and they begin to feel they might be onto something, because firstly, remember that this is a randomized trial. So one would not anticipate any difference amongst the 3 treatments at time 0, because that would be purely a fluke of the randomization. So the closeness of these 3 curves at 0 is to be expected, and it is very encouraging that suggests the trial has been conducted carefully. What will please the people treating these patients is that all 3 of these curves go down. So the placebo patients improve, the haloperidol patients improve more, and the risperidone patients improve even more. Is that clear and obvious? Well, I hope it isn't, because it's wrong. But to see why it's wrong, we're going to need to do a little bit of work over the next half hour. Here's the first way that I've broken down the data to show a potential issue. What I've done now is broken down the data not by which treatment group they were in, but whether they dropped out early, meaning by week 4, whether they dropped out late, meaning by week 6, or whether they stayed the course, meaning by week 8. And you can see here, apart from the fact that there is a lot of variation between the individual patients, because here's a patient in the black treatment group who starts high and finishes low. Here's somebody who starts high and stays high. Here's somebody who starts low and stays low. So that's telling us something interesting. But the thick lines are the averages within each of those dropout categories. And you can see that the early dropouts, on average, dropped out with a higher average response than the late dropouts, and they in turn dropped out with a higher average response than the completers. So this is saying that there's quite a lot of interesting things going on in these data set, which you really need to try to pull apart by identifying and fitting a suitable statistical model and using that fitted model to answer the drug company's questions.
Peter, may I?
Please do, Paolo.
So the colors here have nothing to do with the treatments.
No. What I've done here is ignore treatments, and I've simply partitioned the data according to when they dropped out: early, late, or not at all. Whereas in the previous slide, I'd taken all the patients, irrespective of whether they dropped out, and classified them by which of the 3 treatments they were on. And you can see the 2 pictures are very different.
And the second comment is there is a red line, which is very odd behavior there, right? The one which goes down and then suddenly up, yeah.
Indeed it does. Indeed it does. Okay. And I will be happy to elaborate on that. So would the person who asked that question please remind me, if they wish, if they haven't fallen asleep by then, if they wish to repeat the question at the end of the lecture, because it does illustrate a phenomenon that I think is really quite common in studies of this kind. And I'll be happy to talk about it at the end of the lecture.
That's it for now, thanks.
Okay, now this is a slide which is not just for the statisticians, but I'm going to divert now from pictures to a little bit of algebra. And so I want to say two things. Firstly, to people who are familiar with statistical models, this is really a very simple modeling framework based on one of the simplest statistical modeling ideas of all, namely regression, and furthermore, linear regression. What I also want to say to the non-statisticians is that I will revert to pictorial presentation after a couple of slides. And if you really don't want to follow the algebra, this should not prevent you from understanding everything else in the lecture. But I wanted just to indicate how the models that we fit to longitudinal data of this kind are natural extensions of some of the simplest statistical models you will ever meet, namely simple linear regression, that if you're not a statistician, you may know as the line of best fit in Excel, or you may have used a package like SPSS to fit straight line regressions. And really, we're not doing anything more than a rather sophisticated extension of fitting lines and other curves to data. So what this notation is meant to indicate is that we believe that time affects what we see in our data. In other words, we're interested in knowing how things change over time, which is pretty much an essential question that any longitudinal study will address, because longitudinal means following up over time and seeing what happens. We're going to characterize what we expect to see happening over time as a straight line. So the first Greek letter alpha is the value when t is equal to its average. So t bar is the average follow-up time, and t minus t bar will therefore average to 0, and alpha will be the average response at times at t minus t bar equals 0. The beta parameter, if it's positive, tells you that you expect the response to increase over time, and if it's negative, you expect it to decrease over time. And the Z is the statistician's symbol for noise. Well, it's one of many, but it's the one I use. And that is a random variation between what you expect and what you get. So on the left-hand side, Y is what you get. The Y's here are these dots. These are all Y's. I is patient, T is time. Every one of those dots refers to a patient I at a time T. And you think what you're assuming in this simple model is that what you expect to see over time is a straight line on average, but you recognize that individual measurements are going to be very variable about that straight line. And the need for this subscript notation is because we do have to distinguish between measurements on the same subject and measurements on different subjects, for reasons that I hope my earlier slides have convinced you are sensible, but we'll have another look at that in a few slides' time if you're not already convinced. So that's notation. Now, I can waste most of a slide by simply writing that equation out 6 times. And this would say, I've done a study, rather optimistically, using only 2 subjects, each of whom I've measured at 3 times, 1, 2, and 3. So the average follow-up time is 2. So basically, in this equation, I'm either going to have a -1 when t is 1, a 0 when t equals 2, and a 1 when t equals 3. The first subject, I equals 1, gives me therefore these 3 equations in which what I expect changes, and they also have different random variation. Z11, Z12, Z13, 3 different Zs. We then switch to subject 2, and they have exactly the same structure. They have the same prediction in this simple model, because all that matters is time, and they're also observed at times 1, 2, and 3, corresponding to t minus t bar equals -1, 0, and 1, and they have their own Zs. Now, mathematicians, being lazy people, don't like writing 6 questions when 1 would do. So we use this shorthand notation, which says that Y here is simply a column of all these 6 numbers. Whoopsie daisy, I do that a lot. X is a matrix. It's a matrix which has a column of ones corresponding to this constant parameter, and a column of these values, -1, 0, 1, -1, 0, 1. And this beta without a subscript says this represents both beta 1 and beta 2. And then we have a Z, which indicates all these 6 Zs. Now, at this point, the statisticians will think I'm insulting their intelligence, but I'm quite sure the biologists could present an equally elementary piece of biology that would confuse the statisticians completely. So let's have a little bit of mutual tolerance of people who are expert in one subject and relatively naive in another, amongst whom I include myself, I hasten to add. Okay, so for the rest of this lecture, I'm going to use a minimal amount of algebra to convey to the people with a fairly strong statistical background how we proceed to fit models like this to longitudinal data. So we start on this slide with my shorthand notation, which says that what I observe, y, depends on some input variables x, which in my simple example were just time, some parameters beta that I'm going to estimate, and some random errors z. And the minimal assumptions in this model, for this model to be of any value, are we have to assume that the z's on average are 0. And that's an innocuous assumption, because if they weren't 0, we'd put their non-zero mean into the x. So that's the role of my alpha here, which I've written here as beta 1. It's the same model. So this is saying if these z's had mean 3, I would simply add 3 to this parameter, and now they would have 0. But because we're statisticians, we also want to know about variability. And so the minimal assumption we have to make in order to fit this model to data is to specify the variance of the complete set of random terms z. And when we talk about the variance of a set of random quantities, z11, z12, z13, z21, z22, z23, we mean a matrix because we have variances and we also have covariances, or if you prefer, correlations between different z's. Okay, now, if you have done any fitting of linear models in an elementary statistics course or in your biology or your sociology, the simplest assumption that you will make, and that your software may well make for you, even if you don't want it to, is that these z's are all uncorrelated. So this variance matrix V simply has a value of the variance of the individual z's, which is repeated for each of the z's, and everything else is 0. There are no correlations between different z's. And on that assumption, you can write down what the ordinary least squares estimators are for beta, and it doesn't matter what this is on the right-hand side. This is just a bunch of x's and y's. But the point is there's an estimator which you can calculate very easily and which Excel will happily do for you. And that has some rather nice statistical properties. And the one that's particularly important is that it doesn't matter what the true V is, you will get an unbiased estimator. And that's not a bad thing to have, because it means that you can't be sure that your particular estimator is close to the truth, but you can assume that if you use this method for the rest of your professional life, your estimates will, on average, be the truth, because the ones that are bigger than the truth will be balanced out by the ones that are smaller than the truth by virtue of this universal property that ordinary least squares estimation gives you an unbiased estimator of the so-called regression parameters beta. Okay, but again, a statistician will be very pleased that their estimator is unbiased, but would also like to know how precise it is. And we measure precision by the variability of our estimate. So again, this is just a variance. And if there's only one beta parameter, that's literally what it is. And if there are several beta parameters, it's a set of variances and a set of correlations. And we know what the answer is if we've used ordinary least squares estimation. But in order to get that answer, we have to know what V is. So what that means is that in practice, we have to decide what we think V might look like and then estimate its parameters. Okay? And the point to be really take away from this slide is there's nothing wrong with using simple linear regression software to estimate these parameters in a simple way and get rough, and they will be rough, estimates of the regression parameters beta, but you cannot trust the standard errors because the variances require you to know what V is. And because the software has no intelligence, the software will simply assume that the variance of each Z is a quantity sigma squared, which is the same for all Zs. So what that little piece of cryptic algebra says is that there's a single variance which applies to all of the Zs, irrespective of which subject they're taken on, which person, and at what time they're taken at. So ordinary least squares estimation, line of best fit, LM function if you're an R user, all of these things are actually very useful for exploratory analysis of longitudinal data, but you can't trust the standard errors. That's the take-home message of this slide. What we do in longitudinal data analysis is we postulate a statistical model for that variance matrix. So this is the way in which we indicate that not only do we want to estimate the regression parameters, which tell us what we expect our responses to be, we also estimate how variable the random term is and how correlated different random terms are by another model, which has some more parameters, which I've indicated by the Greek letter phi. And the idea is to simultaneously estimate beta and phi. And if it so happens that when we estimate phi, that corresponds to this simple assumption here, then we can indeed use ordinary least squares estimation to quote standard errors, construct confidence intervals, test hypotheses, etc. I've never found it yet in my professional career. I've never yet found a longitudinal data set for which that is a good assumption. Okay, so normally we have to work a little bit harder and use this more extended model here. And again, if one is au fait with matrix algebra, you can write down what the best, i.e. the most efficient, unbiased estimator is of the regression parameters. And that formula for the best estimate of the regression parameters depends on what you assume about the variance structure. So how do you estimate the variance structure? Well, you do a little bit more algebra and you reduce this overall model to a single function of phi, which you can pass to a numerical optimizer and come out with the best fitting covariance structure, which you plug in to get the best fitting estimates of beta. And you also get their variance by the same kind of matrix algebra that I've shown on the previous slide. So again, you really do not need to worry about this slide, but for those of you who do want to follow up the statistical technicalities, this is really all you need to do to fit any of the models that I'm talking about in this lecture, provided you're careful. And careful is something what one should always be, and I'll come back to that later in the lecture. Now that's going to be it for any fancy algebra. Right, now, the key property of longitudinal data that we need to take account of is the fact that when we take repeated measurements on the same person, so for each person in this study, we take measurements at time 1, 2, 3, 4, and so on. And here's a synthetic data set, purely a simulation, in which I've taken measurements at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 time points. And because I'm looking at the time points relative to their average, we've got a 0 time in the middle, and we're going from -5 to +5. Okay? Now, this looks like the sort of data for which it would not be unreasonable to fit a straight line. And I've already said that, in fact, you can use a simple line of best fit program, and you should get very sensible estimates of the time trend in these data. And you can guess, without doing any fancy modeling, that it should go somewhere through the middle of these points, like that. Now, when I say correlation may or may not hurt you, what I mean by that is that if you ignore correlation, you can get a decent estimate of the trend in these data, but you'll get standard errors for your trend line, which assume absence of correlation. They're not trustworthy, but furthermore, you don't know whether they're too big or too small. So you can't just say, well, I know this isn't right, but at least I'm being cautious, because the standard errors that you get from simple software could be either too big or too small. So you really don't know how to interpret the answer beyond a point estimate, which is a very limited ambition. So what I've done with these data is I've fitted them under two assumptions. And I want to show you the result. That's the fitted straight line. And there's only one line, because actually for these data, the simple-minded line of best fit, ordinary least squares, XL, is identical to what I would regard as the statistically correct way of fitting a straight line to these data, which simply confirms in this example what I said earlier, that you may well get very sensible point estimates from simple linear regression software. But this shows you that there's something else going on in these data. What this picture shows you is something that was less obvious, but was actually there in the real PANS schizophrenia data. This green person is consistently above the overall average, whereas this red person is consistently below the overall average. Now let's just pause a little bit and think, before I show you the answer, what the implications might be for the precision with which you can estimate two quantities in these data. Remember that alpha is the average response at time 0, okay? Beta is the slope of the line. Now, if you just look at the data ignoring the green, the black, and the red jagged lines, you can see that the variability about the line is quite large, right? But you can imagine, and I actually probably should have shown you, well, no, I have shown you actually, if you just look at the green, then you can see that the variability about a straight line within the green points is much smaller. The biggest deviation from a straight green line is much smaller than the overall deviation at any one time point, right? So that suggests that actually, if you fitted a straight line to the green curve and a straight line to the red curve and a straight line to each of the other curves and averaged those, you'd probably get a more precise answer. Now, conversely, when you estimate the average of the whole data set, the naive least squares fitting programs think you've got 20 times 10, which is 200 data points. But actually, you haven't really. You've really only got 1 point from each patient, which is more or less repeated, increasing, but it's tracking, so-called, the way you started from. Now, what that means is when you just do the fitting properly, is that you get 2 sets of parameter estimates and standard errors for the so-called intercept, or in this case, the average response, okay, 5.234, and the slope, 0.493. And so if you think of this line as being averaged at 5 and increasing by 1/2 each unit, you can see that that is indeed a very sensible set of estimates. And as I indicated, whether you ignore the correlation or recognize it, you get exactly the same estimates. But if you look at the standard errors, let's first look at the one that most scientists are interested in. If you use ordinary least squares to estimate the slope of the regression, the average change per unit time, you get a standard error which is nearly 3 times as big as it needs to be, because the correct analysis has a standard error of 0.011 rather than 0.026. But there is no free lunch. There never is in statistics. And if you are interested in the average response, if you ignore the correlation, you will think you've got a standard error of 0.074, and in fact, you're kidding yourself, because the standard error from the correct analysis is nearly 3 times larger rather than 3 times smaller at 0.202. So that's what I mean by correlation may or may not hurt you, because when you recognize correlation in longitudinal data, for some parameters, the standard error is bigger than you would get with a naive and incorrect analysis, but for other parameters, it could be smaller. Now, what that means is that you better have a way of deciding what's a reasonable assumption to make about the correlation in your data. And at this point, we do something slightly ingenious, which at first sight looks a bit mysterious. I actually promised you no more algebra. So I'm afraid I told a lie, but it's a fairly small lie, because what I want you to appreciate is that if you've got data of the form we've indicated, where I is person and J is observation within person, you've also got data on the differences between two measurements on the same person at two different times. Now, don't worry about the algebra. Imagine that you're taking a measurement on the same person, and those measurements are a certain time apart. Okay, here's an example. There's two measurements on the green person a certain time apart. Now, what do you think we would have seen on that green person if we'd taken the measurement at an intermediate time, right? Between minus these two observations here, minus 3.5, minus 2.5. Suppose we take another measurement here. It would have been somewhere pretty close like that. And the variance between, the difference between that one and that one would have been smaller, probably. Suppose I took a measurement immediately after the first one. Well, biology doesn't usually change discontinuously. So whatever's going on biologically in this person, it wouldn't change very much over a small amount of time. So you get an idea that if you actually tried to say, what would I want to assume about how variable the difference is between two measurements on the same person at different times, and what would that variance do as I made those different times move closer and closer together? I think you'd think that the variance of the difference would get smaller, because if they're more or less measured at the same time, you'll have eliminated some of the variability from your comparison. Whereas if you measure them a long way apart, well, they could be all over the place, couldn't they? And this function, which measures the variance of your outcome as a function of how far apart in time two measurements are made of that outcome, is called the variogram. And the reason it's a very useful function is twofold. The first reason is that you can relate the variogram algebraically to what you want to know about in order to fit a reasonable model, which is how the correlation between repeated measurements on the same person changes with time separation. So this is saying how correlated are two measurements on the same person as a function of how far apart in time they are, right? And if how far apart in time they are is very small, the correlation will be very close to 1, and the answer will be close to 0. But if they're very far apart in time, they will be approximately uncorrelated, correlation of 0, and the variability will be our variance parameter sigma squared. Okay, so what that means is that we can estimate our variance and our correlation structure by looking at the sample versions of these observed differences. We can observe the difference between a pair of responses on the same person at different times. Now, some of you will say, yes, but why bother? Because here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 measurements on 1, 2, 3, 4, 5, 6, 7, 8, 9, 20 people. So I could just calculate the sample correlation matrix, and you'd be dead right. And the only reason we don't do that is partly for the reason I showed you at the beginning, that real longitudinal data sets tend to have missing values, which makes estimating a correlation matrix a little bit tricky. But more to the point, a lot of longitudinal studies look like this. This is a study from the early years of the AIDS epidemic in the USA, and these were volunteers who actually took part in a study in which they were followed up over a period of several months, and they were people who were at high risk of acquiring HIV. And they were people who volunteered to be followed up, and those that seroconverted, so-called, in other words, those that initially tested positive for HIV and subsequently initially tested negative and subsequently tested positive, they had their measurement time centered on their presumed time of infection. And because they were aiming to take measurements 6 months apart, 6 weeks apart, This is crazy, actually. That's a misprint. It's not weeks, it's years, because you get very long-term progression in AIDS, in HIV infections. These are years, not weeks, forgive me. So the measurements were on average about 6 months apart, but volunteers don't turn up exactly when you tell them. Sometimes they turn up early, sometimes they turn up late. So whilst you can get a pretty good concentration here of people giving a measurement roughly 3 months before they seroconverted and roughly 3 months after, with the presumed date of seroconversion in the middle, as you move away from that date, you can see the data get very ragged. And there's no way you could calculate a correlation matrix from those data, but you can just as easily as you could for the simpler data set, calculate the difference between any two measurements. And you'd look at the variability of those differences as a function of how far apart in time those pairs of measurements were. And that way, you can estimate the variogram in a situation where it would be essentially impossible to estimate a correlation matrix in any sensible way. But fundamentally, all we're doing is saying, however messy your data are, there is a tool which you can use to get an idea of what a reasonable correlation structure for your data should be before you go on and fit a fancy model. Any questions on that? Because I'm going to show you a variogram. Well, I'll go on for a couple of slides and then I will stop and we can retrace if necessary. So this slide, sorry, Paolo, do you want me to stop now?
Yeah, well, go ahead. I can.
Yeah, I will come back.
Sorry.
So this is the data version of the math slide. This says these are real data points, and I can fit, using ordinary least squares, my regression model and calculate the residuals. And I can just look at pairs of residuals, square the difference, and by multiplying it by a half, I get what I want, which is that the average of all those V's for which the separation distance is U gives me an estimate of the variogram at separation time U, and the average of all of those V's from different people, of which there are a very large number, right, is an estimate of the variance. And what you get is a curve that looks like this solid line. And what this shows is that that variogram curve rises as the time separation increases. So what's happening here, again, don't worry about the algebra. What this is saying is that the closer in time you are with two measurements, the more likely they are to be reasonably close together, and therefore the smaller their variance. And as the time separation increases, so does the variance of the difference increase. And the reason why we don't get zero here, we don't get down to zero, we get to something that's around about 100 units, is because we're dealing with those noisy PANS data. And so even if we could have ethically given the same person the questionnaire twice on the same day, we would have got different answers. And we can actually estimate what we think the difference would have been. We think it would have a variance of about 10, right? Now, this horizontal line at the top is my estimate of the variance in the data as a whole. And so as well as there being something missing here, which is the noise in the data, there's also something missing here. And that I'm going to explicate after I've taken questions by showing you a few simple models of the that we fit to these data, to these types of data, and I'll explain where this missing piece comes from. But what we're basically saying in this picture is if you read the vertical axis, you can say there are three different things going on. There's some measurement noise, there's some variability that's correlated with the correlation getting weaker over time because this curve is rising, and there's something else which will turn out to be variability between different subjects, irrespective of when they're measured. So now I'm going to go back and invite Paolo to say, where do you want a bit more explanation? Or whatever. I'll show the picture because that's the most interesting thing.
I think I'll just re-emphasize something that the HIV example already helped to explain, is the convenience of having the centering for your T in the previous slide.
Yes.
That you can center in a way that gives you interpretability, right?
it's always a good idea for both technical, numerical reasons, and very often for interpretability. Because you're right, Paolo, for me to emphasize it, because what that means is that there will be a parameter in your model which is the average response over the t, average at some arbitrary time, right? And it also helps the stability of the numerical algorithm. So centering your covariates is usually quite a good idea. But it is just about interpretability. It doesn't change the model.
Just to reemphasize, you are decomposing the variance on pieces and bits somehow.
That's right. So as I say, without worrying, and I'm not being condescending here, I really mean it, because what matters in statistics is that non-statisticians understand what's being done, not the algebra that underlies it. And what's being done in this picture is a way of visually decomposing the variability in your data into measurement error, something that's correlated over time in a way that the correlation decreases with increasing time separation within patients. And the missing thing is the variability between patients. So you can think of this as measurement error, variability within patients, and variability between patients. But the extra sophistication is that the variability within patients is not just a parameter, it's a function. And it's a function because the variability depends on how far apart in time the repeated measurements are on the same patient. And as it says at the bottom here, I'm going to explain where we got these fitted curves from in the next few slides.
Okay, Peter, thank you.
So in words, and I've sort of said this, but let me now say it very explicitly, where does the correlation in longitudinal data come from? It comes because there are differences between subjects. And in particular, there are differences between subjects that typically you cannot explain by measured covariates. Now, if the differences between subjects are explainable by their ages, then you put age into your model as a covariate and you have solved the problem. If there are differences between subjects because of their sexes, same applies. Anything that you can measure on each subject is a candidate for a covariate or an explanatory variable. But if differences between subjects persist when you've done the best job you can in adjusting for relevant covariates, that is going to induce correlation in your data. The second term is that measurements do not proceed over time in an entirely predictable way. If they change systematically in time, as here, all of these measurements are showing a tendency to increase over time, right? That's a systematic effect. We put it in the model as a covariate, time. But they're also bouncing up and down relative to that average. And we don't know why that is. Now, if we had another covariate, that might explain why this person had a higher than expected value here and a somewhat lower value next, and then a slightly higher value, and so on. But if we don't have any covariates to explain that, what we then have is unexplained variability within patients between times. And I would like you to think of any regression model, however complicated, as a combination of things that you can measure on the right-hand side and things that you can't measure. And when you write down something and say that it's random, that it has a probability distribution, what you're really doing is saying you don't know what it is. So stochasticity or probability is a metaphor for ignorance. It's saying there is variability in these data that we don't understand. If we can explain the variability with covariates, that's variability that we do understand. And so the ultimate aim of a longitudinal analysis is to explain as much of the variability as you can with things that you can measure and that make scientific sense in context. And what you can't measure, because most biology defies complete explanation, then you put that into the stochastic part. And if your data are longitudinal, you need to work a bit harder than just having a single random component. You need to have potentially 3 random components to pick up differences between subjects, variance over time within subjects, and measurement error. You don't always need all 3, but you have to be prepared to look for all 3. Let's make that specific with some examples. The first source, variation between subjects, has the technical term random effects. If there are any social scientists in the audience, they may prefer the term latent variables. There are several different names in the literature for these, which are actually the same thing, but I call them random effects. Okay. Now, these are characteristics of individual subjects. They're things that a subject carries with them throughout their follow-up period. So if somebody is intrinsically a high responder, that is a random effect, and they'll always be a high responder. If a subject is an intrinsically quickly changing responder, then they will have a random slope with time. Some will have a steep change over time, others will have a shallow change over time. That's a random effect. If we can find out why that happens, we can convert the random effect to a covariate, also called an explanatory variable, and also called a fixed effect. So I always try to think of random effects as missing explanatory variables. They're things that if we'd measured them, we'd have been able to explain a component of variation in our data. And it's our failure to measure every relevant covariate, because we're not omniscient, that we have to allow for the possibility of random effects in our data. So the key thing here is that they are associated with everything that you measure on each subject. The technical term for variation over time within subjects is serial correlation. Serial meaning in order, over time. And as I've now said several times and will now make explicit, measurements taken close together in time are typically more strongly correlated than measurements taken further apart in time. This is not a mathematical theorem. It is a very commonly observed phenomenon. And if your data suggest that it's not true for your data, you shouldn't assume it. But most longitudinal data sets exhibit to some extent this phenomenon. And if you think about natural processes that operate in continuous time, if you take measurements sufficiently frequently, you're more or less bound to have that phenomenon, because real physical measurements don't simply bounce about arbitrarily over time. There is some underlying process going on within the person or the animal or the business or whatever context you're working in, which is changing typically in a continuous, but perhaps somewhat unpredictable manner over time. And the third component is measurement error. And what I've said here is that if your measurements involve delicate determinations, then if you can take duplicate measurements at the same time on the same subject, you'll get two different answers. And the biologists will correct me if I'm wrong, but a lot of biological assay data are actually obtained by taking a sample, say, of blood or other biomaterial, splitting it into two, measuring something on it twice, and taking the average. And if you actually have those two half measurements, you have a direct estimate of the measurement error in the assay. In the context of the example I'm using in this lecture, it's not a delicate determination, it's just a soft measurement. It isn't a hard measurement like blood pressure or weight or height. It's a soft measurement based on a questionnaire instrument which has been validated, but inevitably will include some measurement error which will vary unpredictably every time you use it. Now, the first model historically that included all of these terms was the so-called random intercept and slope model, also called the Laird-Ware model, after the two statisticians, Nan Laird and James Ware at Harvard University, who proposed it back in, I can't remember, the early 1980s. And so what this model says is that every measurement you take has a modeled average, and that there is just what you expect Y to be based on all of your covariates, all of your explanatory variables, all of your fixed effects. But subject I also might be systematically above that expectation or systematically below that expectation, and that will vary across subjects according to a probability distribution, which we usually assume to be a normal bell-shaped curve. The variability over time within individuals is here a straight line, but the slope of that line is randomly varying. Again, if we had a covariate that would tell us what the slope was, we'd plug it into the model. Absent such covariate, we fit another probability distribution, which might have smaller variance, or it might have bigger variance. And we want to estimate that variance from the data. Finally, even if we were able to find out what an individual person's U and W were, we would see repeated measurements varying unpredictably due to measurement noise. Okay, and that gives you a parametric model which encaptures the three qualitatively different components of variation that I would argue any general model for longitudinal data analysis needs to include. It was popular for many years because this often does a very good job of fitting short sequences. And that's for no better or worse reason than the fact that if you just draw 2 points on a piece of paper, you can join them by a perfect straight line. And if you join 3 points, then if these are naturally occurring points on a phenomenon that is generally increasing over time, you can approximate them by a straight line. And as you draw more and more points, or in scientific terms, you collect more and more data over time on the same person, you may well find that the extrapolation of the straight line becomes rather ridiculous. Because clearly, if I believe this to be a model that extends beyond the times that I've observed, then there's no limit on how large, if W is positive, or how small, if W is negative, the model will predict the measurements to be. So it very often fits short sequences well, but it extrapolates in a very odd way. And the technical reason for that is that it assumes that the variance is a quadratic in the follow-up time. And a quadratic function basically funnels out very rapidly and becomes implausibly wide fairly quickly. But it's a good model for short sequences. So what do you do for long sequences? What you do is you replace the random line, in other words, the line with the random slope and the random intercept, with something called a stationary Gaussian process. And what I've shown here is just a nice example in which each of these different colored traces is a very long follow-up sequence from a stochastic process which has all three of my basic components in it. There's variability in the intercept of each curve. These five happen to start together, but there is a definite order to them. And this blue one starts low and it generally stays low for a while, but it occasionally creeps up a bit higher before falling low again, and so on. And then it goes completely bizarre up here, because what's also happening is these processes are varying over time. And by chance, something that starts off low and stays low for a while, maybe by purely random fortune, start to increase, right? And the individual measurements of, you can see they're fluctuating very rapidly, which is a form of measurement noise. Now, the other thing I hope you can see in this picture is that if I just look over a very, very short follow-up time like that, I could fit a pretty good straight line to that. So with short follow-up sequences, even if this is the truth, the idea of a random line fitted to each short follow-up segment would make perfect sense. But with long follow-up, it usually breaks down into something unrealistic. But one doesn't presume this, one estimates it from the data. So let's now postulate the model that I'm going to use for my PANSS data. I am going to allow each person to be intrinsically a high or low responder. I'm going to give them one of these Gaussian processes, one of these erratic traces, to measure that person's individual deviations from their own personal average relative to what I would predict based on their treatment, 1, 2, 3, and the follow-up time, 0, 1, 2, 4, 6, 8. So this is where I describe the average response over all patients. This is whether an individual patient on average will be higher or lower than the average of all patients. This is whether an individual patient's measurement, or rather their true state of mental health, will be higher or lower than their personal average. And this is the noise which corresponds to the variability I would see if it was ethical and practical to administer the questionnaire twice to the same person at or very close to the same time. And then we have just a bit of algebra just to hold the algebra together for those few of you who wish to follow the algebra. And I want to emphasize that this model is pretty flexible, but for some applications it's too flexible. And in particular applications, you may find that one or two of these three components dominate. And unless you have a lot of data, it's quite difficult to fit the full model and you have to make some pragmatic simplifications. For example, by ignoring the stochastic term here and saying it's just random variation about a mean for each person. Sometimes there is no average difference in the average between people. There's just a lot of variation over time. Sometimes the measurement noise is negligible, right? So you can simplify your model if and when the application merits it. Okay, so I think at this point I'm going to go back to, not quite, firstly I'm going to translate that general model into the variogram. So this is the theoretical variogram of the model I've just shown you, in which this horizontal band here is the measurement error variance, whoopsie daisy, and that's one of my three variance components, Greek letter tau squared. This curve starts here and finishes here, and that vertical distance is the variance over time within a subject, Greek letter sigma squared. That flattens out because the correlation between repeated measurements within a subject decays to zero, typically. Doesn't have to, but typically it does. And there is residual variability between patients, which is the third variance component, Greek letter nu squared. And so now you can see that if you can estimate a variogram from your residuals, in other words, after fitting your mean value parameters, your treatments and your times, then if you find a curve that fits this template, roughly, it'll be jagged, as I've previously shown you, then you've got a reasonable structure for your data. So the goal is to do a preliminary analysis using ordinary least squares, calculate the empirical version of the variogram, compare it with this theoretical template, and adjust the theoretical template by changing the correlation function and the values of the three variance components. And by the way, Paolo wrote a very nice interactive version of doing this many, many years ago in the geostatistical software package that he wrote. And when you think you've got a reasonable fit, then you can fit the model using software, which is only slightly more difficult to use than line of best fit software. I'll say a very little bit about software at the end of the lecture, which is not far away. So this is the non-mathematical slide about how we make this work in practice. The statistical principle we're going to use throughout is that likelihood-based inference is a statistical gold standard. You don't need to know what likelihood-based inference is unless you wish to, but what you do need to know is that under very general circumstances, and in particular for all of the models I've discussed in this lecture, using the likelihood-based method of inference will guarantee you, in large samples, efficient, i.e. small variance, unbiased parameter estimates. The method for estimating parameters is called maximum likelihood. The method for comparing models is called likelihood ratio testing. And for those of you who are statisticians and would rather use Bayesian methods, feel free, they're still based on the likelihood. So the red is true for all statisticians. Whether they implement it using maximum likelihood and likelihood ratio testing or Bayesian inference is a matter of choice within the statistical community. Now, the thing that I've conveniently forgotten about, since I emphasized it right at the beginning, is that the treatment of missing values needs care. The practical point to make is that if you think that this framework is relevant to your research and you want to actually use it, there are plenty of software implementations available. In particular, an R function in the package NLME and in its more modern successor LME-R or LME4, and in the SAS proc mixed routine within the SAS software system, you can fit these models just as easily as you can fit line of best fit models. But I really want to hammer home that we have to be careful. So before I go back to the PANS data, are there any questions or things that people would like me to repeat for additional clarification?
Peter, I'll just mention two comments that you can either talk about them now or later, is about the extent of the longitudinal data. What is a long series, what is not a long series, what it means, yeah, unless you have a lot of data, as you said. So it's on your convenience where you want to place this discussion.
I will answer that one now. Is there another one?
No, that's it.
Okay, so I'll go back to this. The words short and long are really not strictly correct. A series with 50 follow-up measurements is short if the trajectory of the measurements is roughly linear, because it's short in the sense that you can give it a short explanation, namely it's approximately a straight line. A series of 10 measurements is long if you can't give it a simple explanation. If it changes erratically, okay, then a straight line is not enough. So really, nobody's asked me that before, curiously, and I think I won't use those words again. What I mean is, if when you look at your data, which you should always do, and if in particular when you look at the residuals from your ordinary least fit to your model for the mean response, you can convince yourself that the individual longitudinal trajectories are well approximated by a straight line, and this is your model of choice. Right? And you will do a very good job, and you will have very rapid computations, and your inferences will be pretty robust, provided that fundamental assumption is a reasonable approximation. If you have data like this, you will get very bad results from that simple model, because essentially it'll just estimate the trajectories as, you know, that's not really a decreasing trend. It just so happens that here it was slightly increasing, here it was decreasing, and there it's increasing again. So it really is a matter of choosing your model to fit your data, rather than looking for, let's say, a rule that says if your follow-up contains 10 observations, you should do this. And if your follow-up contains 20 observations, you should do something different. What you should do is recognize that your model needs to be not obviously qualitatively wrong for the variability that you see in your data, right? And provided it's not qualitatively wrong, there is virtue in keeping it as simple as possible, because simpler models can be fitted both more robustly and more efficiently than complicated models. But if the world is a complicated place, there is no point in pretending it's a simple place. If it is simple, exploit that simplicity, you will get robust, efficient estimates. If the world is complicated, you have to deal with the complication.
Spot on, Peter. Thank you.
So back to our data. So let's fit our model to the data and let's see what happens. That's what happens. So when we fit the model to the data, you can see that we've modeled the mean trajectories actually as quadratics. That's not a much better fit than a straight line, but it is a significantly better fit. So I wanted to give the model the opportunity to tell me if they thought the effect was waning over time, or if it was indeed continuing to decrease. It was sure as hell isn't going to decrease indefinitely. And in particular, this black quadratic is not going to increase indefinitely, or it would become physically ridiculous. Whoopsie daisy. But provided I don't extrapolate beyond the 8 weeks, that's my fit to the data. Okay. And what I want to show you, for those of you who have always been skeptical about so-called placebo effects, is that my best guess for the placebo response is actually flat. It's got a curve to it because I've fitted quadratics, but in effect, that's a flat line. So this analysis is suggesting that there is no placebo effect. This black curve is suggesting that haloperidol does have some effect, and this blue curve is suggesting that risperidone has a bigger effect, which was joy to the pharmaceutical company's heart, because what they were hoping for was demonstration of an improvement of an average of 20% over this 8-week follow-up period. PANSS is in effect a percentage. It's not strictly a percentage, but it's a score on 0 to 100. And the average seems to have gone down from something close to the high 80s down to something close to 70. So not quite 20%, but getting close, right? So a good result. But looking at that picture, you might say, how can that be? Those curves simply don't fit the data. And I will tell you an honest story. When I was doing this work with the American pharmaceutical company, I was in America, and the software I was using was not what a modern, fully developed piece of software. It was an experimental piece of software that my postdoc back in England was using. And when I drew this picture, I actually got on the phone to him because it was so long ago I couldn't email him. And I said, there's a problem with the software. There must be a bug on it because it's giving me ridiculous results. It wasn't. It was giving me the correct results. So how come? How can this be right? And I hope this slide tells you how it could be right. Because here I've plotted another very artificial data set in which the explanation is very simple. The explanation for this data set is that nothing changes. Each black line is the true state of the thing I'm trying to measure over time on a patient, and I can measure it perfectly without any measurement error, and it never changes. All right. To a first approximation, it could be the height of an adult who doesn't have any bad accidents and isn't old enough to start shrinking. All right. Here, another patient, whoopsie daisy, and so on. Right. So, whatever this is that's being followed over time, the right interpretation is that it doesn't change for anybody. So what's happening? What's happening is that for reasons unknown, because this is a simulation, people at the bottom end of this response disappear very quickly. People who are at somewhat intermediate range tend to disappear later. There is some randomness here. They don't all disappear at the same time. Some of them go a little bit early and some a bit late relative to their peers. And some of them stay the course. The ones that stay the course are the ones who are generally giving a very big response. So if I simply took the average of all of the red lines, at this point, the average would be somewhere in the middle, about 0.5. At this point, it's gone up to about 0.6 or 0.7. And at this point, it's gone up to 1. So that's exactly what was happening in these data. What was happening is that the people who were dropping out early were dropping out primarily because the treatment was not helping them. So in this case, the curves that we observe are going down because it's the high responders that are dropping out. But the curves that we're fitting are what we would have seen if those people had not dropped out. Because if you apply the statistical gold standard of likelihood-based inference to these data, what you get are these quadratic curves. And if you use SAS-Prop mixed, or if you use the R packages NLME or LME4, this is what you get, whether or not you want it. Because what it's doing is fitting a mean that has the following interpretation. It's the hypothetical mean that you would have seen if nobody had dropped out. Now, if you're of a philosophical bent, you might wish to consider how you would interpret that if the dropouts were actually people who died. Now, these are not people who died. These are people who were still there 8 weeks after, still suffering from chronic schizophrenia, but they had not complied with their medication. So hypothetically, they could have done. If they're people who've died, it's an interesting philosophical question as to what you're trying to estimate as what somebody would have responded to if they hadn't been dead. The key for this slide, and we're nearing the end now, is what are you estimating when you have longitudinal data with incomplete values of observations, and in particular of dropouts? And there have been some simple ways of dealing with dropouts that have been around for a long time before these longitudinal models were developed. And two of the more widely used and still sometimes used are the so-called completers only strategy, which says just analyze the data from people who comply with the protocol and stay the course, don't drop out. So what you're doing then in mathematical terms is estimating a conditional mean. It's what you would see in the subpopulation of people who complete the protocol. And for some studies, that's what you want to know. So that's what you should estimate. Even more common in randomized trial world is a method called last observation carried forward. Now, in last observation carried forward, it's not at all clear to me what you're estimating. Last observation carried forward would do exactly the right thing in this very simple example, because it would simply extend all the red lines to the right-hand side of the diagram. What it would do for the PANS data is much less obvious. It would extrapolate these dangling ends of lines here. And what you can see, and I promised I'd come back to it, is that actually most of the dropouts, these dangly ends, are at the top part of the diagram rather than the bottom. So what I think is happening with these data, and what I've discussed in much more detail in the book, is that actually these people are dropping out not just because they've got high symptoms, but because they're actually feeling worse. And so very often if a patient starts feeling worse, they drop out. So you need to deal with that. So in likelihood-based inference, which is what I said earlier, what you are estimating, whether you wish to or not, is, well, with these models, is the expectation of Y in a hypothetical dropout-free population. Now, you don't have to do that, because you can go beyond what I've talked about in this lecture, and I haven't got time to do it. In fact, some of you will think I didn't have time to do what I've done, because you must be getting ready for your lunch, I suspect, or your tea or something. But dropout mechanisms have been studied extensively over many years, and a very useful way of thinking about different dropout mechanisms, although I don't like personally the names, the ideas are very important. What's called missing completely at random says that the random variation in the data, Y, and the random variation in the dropout times, D, are independent random processes. So dropout has nothing to do with the measurement process, okay? This second classification, MAR, is called missing at random. And the reason I don't like the terminology is it doesn't mean missing completely at random. It means something technical, which is that the Ys that you don't see, right? They exist mathematically, but you don't see them because somebody's dropped out, are conditionally independent of the fact that they're missing, given everything that you've seen so far. Now, that's a technical set of words, and the informal counterpart of that is saying missing at random means that you can predict what you would have seen when somebody drops out from what you've actually seen before they drop out. And if the data are correlated in time, that's a true statement. Missing not at random is still random in the sense of stochastic, and it means neither of the above. Okay, so when I said that if you fit these linear models to longitudinal data using standard software like R packages for mixed effects models or SAS prop mixed, what you're doing is assuming MAR. And under that assumption, you are estimating Y in a hypothetical dropout-free population. Now, it turns out that provided you've got strong serial correlation, that's a pretty good assumption. It's not always true. It certainly isn't something that is an innocuous assumption. You should critique it in your mind and be prepared to contemplate a more general form of model, which allows the most general assumptions of all about dropouts, which is that they're missing not at random. And in order to do that, you really need to work very hard, and you need to model not just the data that you've got, but you also need to model when people dropped out. Now, we know how to do that because you've already had a lecture on survival analysis from Sylvia Shimokura. And you can think of a dropout time as a survival time, except that in design studies, it's usually discrete. In the PANS data, it had to be 1, 2, 4, 6, or 8 weeks. But you could equally get a study in which people drop out, and in particular, if they die, they certainly drop out at any random time. And you want to jointly understand the two stochastic processes that drive what you see in the measurements and when you stop seeing it because they've dropped out. And if you have that completely general framework, you really do have a very powerful methodology at your disposal because you can estimate whatever you want. You have a complete description of the data, both the data that you intended to get in a dropout-free population and the data you've actually got, and you can combine the information in whatever way you want. And it's things like that that keep statisticians in a job, because if MAR always did the trick, you could all probably do your own longitudinal analyses, irrespective of your disciplinary background. Okay, now I've probably taken too much of your time, but I wanted to leave you with an opportunity, if you wish, to actually try analyzing a subset of the PANS data using whatever software you wish, but I use R, so I've suggested you might want to use R for this, and investigate for yourself whether the sort of things that I've been saying in this lecture are reasonable for these data, and convince yourself that it would not be difficult to use the same methods on your own data if and when you wish to do so. But at that point, I want to thank you very much for your attention, and that is the end of the lecture.
Great, Peter. Thank you so much. If we can elaborate a little bit, there are two sorts of, let's say, studies that you illustrate with your slides. One are more like planned studies, like the drugs example, whereas the other is you get what you get, like the HIV example, where you are not able to design things. So think about the first category. There are obvious design issues regarding replicating more subjects or replicating more observations over times and so on. So I wonder whether you have some kind of general comments on the design of longitudinal studies.
Yes, and of course, both of those studies were designed, but the point is that when you're dealing with human volunteers, you can't insist that they behave in a regulated manner. And of course, there is a third category of study which is genuinely not designed. And if the study is genuinely not designed, it's simply observed, then if you think about it, the idea of a dropout is a rather strange one, because if you didn't say in advance when you wanted to take a measurement, you don't know whether it's missing or not. So the third category, which I'm not going to talk about in detail, but I just tease you as something to think about, is that how would you model data in which you wanted to model measurements Y and non-dropouts? In other words, the times at which you take measurements are also a random process. Now, you know, Paolo, that there's an analogous problem in geostatistics that you could talk to the students about locally should you wish. But I will confine myself to those two studies you've indicated where they are designed studies, but in one you have more control over what patients actually do. And what you do is you say, okay, I can imagine this scenario, and I'm going to call it the Johns Hopkins sample size scenario, because the Johns Hopkins sample size calculator consists of the following. Question 1, this is the statistician talking to the scientist. How big is your grant? Question 2, how much does each datum cost? Divide one number by the other and you have the sample size. End of story, right? Now, it's not the end of story for longitudinal data, because then question 3 is, should I take a lot of measurements on a small number of subjects or a small number of measurements on a lot of subjects? And what it boils down to is the balance between these three variance components. So basically, under any postulated model of this kind, where you have a parametric model for the covariance structure, you can derive the formulae for the efficiency with which you can estimate the parameters of interest as a function of those model parameters. So as in any design calculation, you have to make assumptions about reasonable values for those as yet unknown parameters, plug those assumptions into a simulation, simulate data, fit your model to the simulated data, and from the output, look how precise your estimators are. And the other general point I want to make about this, what I'm suggesting there is, I think most sample size calculations should not be about achieving a prescribed power to reject a particular null hypothesis. Sample size calculations should be focused on the precision with which you can estimate an interesting parameter. Because if you ask a biologist to estimate a parameter, I'm sorry for the others talking about biology all the time, but that's what I do. It's the only thing I understand. A biologist will usually know what a parameter means biologically, and they will know what a usefully precise estimator is. And so if you say, okay, what's a usefully precise estimator? And they say plus or minus so-and-so, then you can work out using the method of simulating your model under different assumptions about how many observations you take per person and how many people you take, what you have to do to match the useful precision at the minimum cost. Frankly, I've never understood why anybody cares that to design a study that has 80% power to detect a deviation from a null hypothesis which is specified arbitrarily. But I can see very easily why people want to run studies and be sure that a parameter that they care about can be estimated with a useful degree of precision. So the basic story is, look at the cost constraints, not perhaps quite as simply as the Johns Hopkins model. Within those cost constraints, know what's a useful degree of precision, see if you can achieve that degree of precision, and if you can, see how if you can do better than the minimally useful precision by adjusting the balance between observations per person and number of persons in the study.
Great, Peter. I have a slightly more technical question for you. Yeah. And I don't know whether Wagner is with us now, but he's asking whether you could comment on inverse probability weighting and yes, for type of missing data it could be useful.
Recall when I said when I first saw these estimates, I thought they must be wrong, right? Now, There's a completely different approach to analyzing data of this kind, which was initially proposed by Scott Ziegler and Kung-Hee Liang in 1986, called generalized estimating equations. And what they do is, now they do more than this, but a simple way to explain it is they say, just fit by ordinary least squares, but then estimate the residual correlation structure and adjust your standard errors accordingly. Now, if you do that, you will get fitted curves that, roughly speaking, go through the data. You'll get 3 smooth quadratic curves that roughly follow the blue, the black, and the red lines. And the reason you do that is because you are estimating the conditional means given that you've not dropped out. And as I said in one of my last slides, that's different from trying to estimate the mean that you would have seen if nobody had dropped out. Now, that original generalized estimating equation method assumed missing completely at random, the simplest form of missingness, whereby the missingness has got nothing whatsoever to do with the process you're measuring. Now, subsequent to the Liang and Ziegler work, people who work predominantly but not exclusively by any means in the randomized trial area wanted to be able to estimate parameters in models of this kind under minimal distributional assumptions. So they wanted to be able to use estimating equations that weren't tying the analysis down to a very specific stochastic model, but at the same time could produce more robust standard errors than were provided by the original Liang and Ziegler form of generalized estimating equations. And so they would be then bringing in things like inverse probability weighting as a method for adjusting your weighted least squares calculations to allow for different dropout probabilities as a function of patient characteristics or patient history. And so that was getting to be more in the spirit of MAR, but in a technical sense, it was still not committing to a specific parametric model. It was actually producing estimates that were consistent under the minimal, what you might call structural assumptions about the relationship between missingness and observed data, rather than a specific parametric model for the relationship between them. And again, I would say that the more messy and the larger in terms of follow-up your data set is, the more I would say that you really need to grasp the nettle and fit parametric models. But for well-designed experiments in which relatively simple things go wrong, the modeling could be considered, if not an over-elaboration, then certainly an unnecessary sophistication. I don't feel strongly about it, but certainly in a randomized experiment with a small number of follow-up times, and at the very least, a close monitoring of when missing values occur, why they've occurred, I think you can get pretty far with weighted estimating equations. But if, particularly in studies that are more quasi-observational, there are really a lot of unknown things going on, then the richness of the stochastic modeling framework, I still think, has a lot of value. And in particular, one thing you can do with stochastic models, which you can't do with inverse probability weighting, is make individual predictions. So in one of, I'll take you back to the AIDS data for another historical story there. At the time these data were collected, every patient whose CD4 level fell below a prescribed constant was immediately put onto AZT therapy, antiretroviral therapy. That drug therapy was of time-limited efficacy. And if you simply fitted naive least squares lines to the data, you were putting patients on AZT far too early. Whereas if you make stochastic predictions based on fitting models to the individual trajectories, you could show that even a patient whose observed CD4 count was below the intervention threshold, you could see that actually their underlying true state was above that threshold and remained above it for a considerable amount of time. And that case study is in the book with Kung-Hee, Scott, and Patrick. So I really think it's not about saying this is the one way you should analyze longitudinal data. It's about following the general paradigm of saying at the top of the heap, the most important thing is ask the right question, or rather, for the statistician's point of view, answer the right question, which is not your question, it's somebody else's. The second thing is, if you have the luxury, design the study within any practical constraints to allow you to answer that question as efficiently as possible. And the third thing is to analyze the data efficiently. And the efficiency, in the sense that I've been talking about it in this lecture, necessarily comes at the price of being willing to make parametric assumptions about the variability in the data. And if you're in a situation where you don't wish to do that, then you have to use estimating equations, and you are in a different world. I mean, it's not really a different world, sorry, a different part of the same world.
Excellent, Peter. Peter, you said something, and I must disagree with you at least once. You said you were taking too much of our time, and that's certainly not true. I learned throughout my life that too much of Peter is never too much. So I want to share with my colleagues and the audience that it's really enjoyable. Read your papers, read your books, and listen to you at your lectures. There is a lot in every single sentence. I learned that very early in my first contact with you and your texts, that you are well capable to place lots of ideas in a very objective way, and you say a lot in one sentence. So I'm sure several people, including ourselves here, will be looking at this video again and again, and will be very helpful. And you make beautiful connections with our former lectures on sampling and regression models, also with longitudinal data and survival analysis, putting all together in a big picture. So I will say thank you so much. I know that it's dinner time in the UK now, so it's quite late there. It must be close to 8 o'clock in the evening there. So thank you so much. And I guess we'll see you again in 2 weeks' time.
Yeah, so no, thank you all for your patience, and I will look forward to seeing you again in 2 weeks' time. Some of what you've said about me is true, Paolo, but by no means all of it. But it's been a pleasure, and one I'll be very happy to repeat in 2 weeks' time.
Okay. So with these words, if the students have any further questions for the future, I'm pleased to try to ask them later. So for now, I will say thanks again to Peter. Have a break for the students, and we come back in 20 minutes time for the follow-up of this evening. Peter, all the best.
Thank you.
See you soon again. Thank you so much.
Thank you, and I'll see you in 2 weeks' time. Goodbye.